Okay, so in this hour we will be discussing the Bernoulli's equation. Now the phenomena that we would like to study is basically this one. If you just take two foils, two very thin sheets, put them separate with each other, and just if you blow in between them, you will see that they just move together. They get closer. So if they are getting closer, it just means that there should be some force acting on them. And in terms of pressure, if you compare the force acting on these areas will be created by pressure, or if there is a force, we can define a pressure. And the pressure outside so the pressure outside these two foils should be greater than the pressure inside. Now the pressures are equal, but if for some reason if you blow in between, the pressure gets smaller inside. So that's what we will try to understand. Now we will we will still assume a steady flow. That is, we will have streamlines. So this might be some region of the liquid which is flowing. There is gravity. This is the direction of G. So the two regions, their height, let's say it differs by h. Here we have pressure P1. And on the other side we have, let's say, pressure P2. And here we have the velocity V1. This is the flow velocity. Here we have the velocity V2. The speed. Again, if we just wait for a very small amount of time, let's say this area will just move in the direction of V1, and it will arrive at this point after dt. So this length over here is nothing but V1 times dt. And similarly, this area over here will move along in the direction of V2, and it will come over here. And this length over here is V2 times dt. Now let us look at the change in the energy of all the liquid within this volume. So this was our initial volume. So this is our initial volume. Then this initial volume moves such that this area becomes this one and this area becomes this one. There is work done on my system. The work done is due to the pressure. At this area, the pressure is pushing it in this direction. The total force is A1 times P1. Let's say the area is A1. On the other side, the area is A2. Here, the force is A1 times P1. The work, we are calculating the total work done. A1 times P1. This is the force. And under the influence of this force, this area moves by a distance V1 dt.
Which area are we talking?
This red one over here. Okay. Initially it is over here, then the pressure pushes it, it reaches this point. So this is the force acting on that area. This is the distance that area had moved. So this is the total work done by the pressure on this area. On the other hand, if we look at over here, the pressure is pushing it in this direction. In this area, the pressure is pushing it in the direction of the motion. Here, the pressure is pushing it in the opposite direction, so the work done by this force is negative. This is minus A1, A2, P2, V2, dt. A2, P2 is the force acting on this area. V2 dt is how much the distance that force acts. So this is the work done by the pressure on this side. So this difference is what gives us the total work done on our volume, on our liquid. Yes. Because on this area, the pressure, the outside pressure, of course there is the inside pressure, but since this is my system, I'm calculating the work done on my system by external forces. The outside I'm pushing in this direction. This is the direction of the force of the pressure, and the area is moving in this direction. They are pointing in opposite directions, so that is why we have this minus sign. The displacement is in the opposite direction of the force. At this region, the pressure is P1. If you look at the internal, now this is the force that is acting on my system from the outside. Just imagine it like this. In the break, you just accumulate at the door. Let's assume that all of you rush there on the door, and I am pushing you from inside to outside. Of course, you will be pushing me back, but that's not the work done on you. I will be doing some work on you, so I'm pushing you out. That is the positive work. And let's say somebody outside who tries to prevent you from going out, he will try to push you back in. Of course, you will be pushing him back with the same force, but again, that is not the work done on you. So the other guy outside is trying to push you back in. And this is the total work done on you. So this is the total work done, which is equal to the change in the mechanical energy of the system. So this is the work done by the non-conservative forces, and the total work done by the non-conservative forces is equal to the change in the mechanical energy. Now, the change in the mechanical energy, it has both two parts, the kinetic energy and the potential energy. But you see, in this green volume, there is this part excluding this one that doesn't change. So this part is the same initially and finally. Since we are talking about the steady flow, the velocities did not change, so the kinetic energy in this region is the same at the initial and final state. The potential energy is the same because the position did not change. The only thing that changed is this volume of liquid had disappeared. So the corresponding kinetic energy, there was a reduction in the corresponding kinetic energy, there is a reduction in the corresponding potential energy, and this region has reappeared. So there is a corresponding increase in the kinetic energy and increase in the potential energy. Let's look at this region. The total volume of that region is A2 times V2 dt. That is the total volume. This is equal to A2 times V2 dt. This is the volume. This is the density. So this is the total mass of that volume. And that volume is moving with speed V2. This is the total mass of that volume. 1 over 2 mv v2 squared minus 1 over 2 a1 v1 dt rho v1 squared. This region, this volume I don't have anymore in my region. So there's a reduction in my mechanical energy by this much, and there's an increase in the mechanical energy by this much. If we also add the change in the potential energies, this was the mass I have multiplied by GH. This is the potential energy of the new region, minus 0. So what I did, the change in the mechanical energy. This is a new region that appeared. The kinetic energy of this region is the volume of that region multiplied by the density, which gives me the total mass. 1 over 2 mass times V2 squared is the kinetic energy of this region. Plus the kinetic energy of this region is the final kinetic energy of my system. So the kinetic energy of all this thing, whatever that is, I don't know, plus the kinetic energy of this region is my final kinetic energy. My initial kinetic energy is the kinetic energy of all this region plus the kinetic energy of this region. Now if I take the difference, what remains is the kinetic energy of this region minus the kinetic energy of this region. And kinetic energy is 1 over 2 mv squared. I know the volumes of these two regions, so I know their masses. I know their speeds. This has speed v2, this has speed v1, so I can calculate the change in the kinetic energy. And I can do the same for the potential energy. The final potential energy is the potential energy of this region plus the potential energy of this narrow region. This is the final potential energy. Well, the initial potential energy is the potential energy of this region again plus the potential energy of this small region. If I take the difference, what remains is the potential energy of this narrow band over here minus the potential energy of this narrow band over there. Yes, your question. I mean, we are assuming that's steady flow. That's a strong assumption. So this shape never changes. So the water group over here will move along this line. The water group over here will move along this line. The shape almost doesn't change.
Why did you say minus that in the next one?
Which one? Well, because we are trying to calculate the change, well, this delta W is the change in the mechanical energy of the whole thing. Because there is this external force acting on external forces acting on my system, and the total work done by the external forces will be nothing but the change in the mechanical energy of my system as a whole. Of course, that might be changing, I don't know, the kinetic energy of this particle by some much, of this other particle by some other amount. I don't know, I don't even care. Because I know that the total mechanical energy done on a system is equal to the change in the total work done on a given system is equal to the change in the mechanical energy. Total work done by non-conservative forces. That I know, that's what I'm using. Other questions? It's clear, is it? Yes, question.
Why is the first part not second part minus
Well, let's see. Let's rewrite it more explicitly. Let me take all this region. Okay? Let's say that let me use some color code. This green region has kinetic energy 2, potential energy 2. The whole thing, all of this green region has this region has kinetic energy 2, potential energy 2. Now this region, let's say we have kinetic energy 1, potential energy 3. Kinetic energy 3, potential energy 3. And in this region, I have kinetic energy 1, potential energy 1. For the time being, I don't know what their expressions are, but let's say that the total kinetic energy in this volume is this one, the total potential energy of this volume is this one, etc. So what is the initial kinetic energy of my system? Initially, my system has this region plus all this region. So initial kinetic energy is kinetic energy 1 plus kinetic energy 2. This is my initial kinetic energy. Because initially, the volume, the liquid that I am considering is in this volume over here. This one plus this one. And the initial potential energy is potential energy 1 plus potential energy stored in region 2. Then I mean, the water is flowing, the liquid is flowing, everywhere is filled with fluid. So as this fluid, the fluid over here flows in this green region, there will be other fluids filling this volume, but I don't really care. I mean, I'm just looking at a specific amount of fluid as they are flowing. So when my fluid has moved by some amount, by this V1 delta T over here and V2 delta T over there, the final kinetic energy of my system will be the kinetic energy of this region, energy 2 plus kinetic energy 3. Here I'm using the fact that the flow is steady, which basically means that if you don't go with the flow, if you just stay and look at a fixed volume, the liquid in that volume will change as the liquid is flowing, but the velocities will not change, so the total kinetic energy in that volume will not change as the water is flowing. So that's why I can use the same kinetic energy 2 in the initial case, initial time, and the same kinetic energy 2 after some amount of time. It will not change. And the potential energy final will be potential energy 2 plus potential energy 3. Now, if I calculate the change in the mechanical energy, that the mechanical energy is the sum of these two, and the sum of the kinetic energy and the potential energy. Now, if I take the change in the mechanical energy, or if I look at the change in the kinetic energy, the final kinetic energy minus the initial kinetic energy, this kinetic energy in the second region, they just cancel. I have kinetic energy 2 over here, kinetic energy 2 over here. So what is left? The change in the kinetic energy of the system as a result of the external forces acting on my liquid will be the kinetic energy of this narrow region minus the kinetic energy of this very narrow region, this KE1. So that's why I'm only subtracting the kinetic energies of these narrow regions, because the kinetic energy of this larger region, it just cancels in the difference.
They are the pressure of the water.
Yes, at this point and at this point.
We find that them like external forces.
Okay. fluid.
I think they are external forces only.
Well, you see, external is a concept that depends on what you call your system. Take this water. If you just choose some point, there's a pressure over there. If you imagine a volume around that point, well, the volume will have some surface, and that surface will feel some force, external force due to the pressure of the external liquid. It's just a...
Our system, in this case, our system is
My system is this one. At the initial time, my system is in this green region. It's moving, so plus it's changing its shape. Its shape will also change since it's liquid. And this is the initial my system. After some time, it just becomes from here up to here and back. Three. I mean, in fact, we didn't make any assumptions about the dimensions anyway. I mean, we didn't make any assumption on the dimension. Okay, so this is, here we have this equality. This expression over here should be equal to this one. Now we can do some cancellations. So this whole thing is equal to this one. Also remember one thing, there are what we had derived before. So if you have such a flow, the cross-section and the velocity, their product is constant. It basically tells me that A1V1 is equal to A2V2. So let's see, I have A1V1, A2V2 which is equal, A2V2 which is equal, A1V1, A2V2. They are all equal to each other. We had just derived that before, so I can cancel that. So this terms, these ones, they will just drop. Well, dt, all the terms have dt. I can also cancel dt's. So let's see what is left. P1 minus P2 is equal to 1 over 2 rho V2 squared minus 1 over 2 rho V1 squared plus rho G. Let me write H as H2 minus H1.
I understood why you canceled the A1 ones,
Which one?
the A2B2 potential energy.
Why not?
How?
A2V2 is always, I mean, here I have the sum of three terms. Each one is proportional to this AV. They are all the same. So I can cancel them. Now let me reorganize this a bit. P1 plus 1 over 2 rho V1 squared plus rho GH1. This is equal to P2 plus 1 over 2 rho V2 squared plus rho GH2. This is the final expression we have. the pressure at a given point, add 1 over 2 the density times the speed at that point squared, plus the density, the gravitational constant times the height of that point. If you evaluate this expression at one point, and if you evaluate it at a second point, they should be equal. Well, these points 1 and point 2, I have chosen them to be this point and this point, but they are kind of arbitrary. I could have chosen any other point along the streamline. But if I can choose any other point along the streamline, it just tells me that this combination should be the same along the streamline. P1 plus 1 over 2 rho, no, not P1, P V squared plus rho G H is constant along a streamline. So this is called the Bernoulli's equation. Now let's see, does it explain this phenomenon? So we said that, okay, initially we have the plates, they are vertical. If I don't flow in between, if I flow in between, they move together. So how can we understand this phenomena from this equation? Well, the flow is horizontal, so H doesn't change. H is constant. But speed is different. So if you just compare, let's say, this point and this point, since I'm flowing in between, the speed becomes larger. If the speed becomes larger, this combination should be constant. If the speed becomes larger, the pressure should drop. So that's why these leaves move towards each other. The pressure in between just is smaller than the pressure outside when I blow it. Now there is one experiment you can do even at home. Probably most of you have some hair dryers. Get your hair dryer, find a table tennis ball, and make the air dryer blow air upwards, and put the table tennis ball in between. You will see that it will not fly away. It will go up and it will stay there. Give it a try. I forgot to bring it today. Well, do you have a hair dryer with you? No. Now, questions on this one? Any questions? Okay, so let's imagine we have a bottle filled with our liquid. And you create some holes. One hole here, another one over here, another one over here. Of course, the water will start leaking out. Let's say this is hole 1, this is 2, this is 3. Now, which one do you think will have the longest range? Number one. Well, about the longest range, I'm not sure. The range depends on many things, but it will have the largest horizontal velocity. This one. This one will have a smaller, this one will have a smaller horizontal velocity. Now let's see how we can calculate this velocity as a function of the height. Of course, it will be related with pressure. So this is our bottle filled with a liquid. And this is the hole. It is at a height, at a depth h from the top. Now we will use the Bernoulli's equation, but remember Bernoulli's equation is valid on a streamline. So we should first identify some streamline that passes through this point. Well, we can just sketch one. This will be the streamline that will pass through that point. And it will come out and it will go some distance. This is our streamline. And Bernoulli's equation tells us that along this streamline, the pressure plus 1 over 2 rho v squared plus rho g h, this should be constant. So let's write this expression for the top point. For this point, let's say the outside pressure is P0. What is the pressure at that point? P0 plus 1 over 2, the density, we are looking at incompressible fluids rho. Well, the speed, you can say that, okay, this is a very small point. It's very narrow. The area can be quite large, so it's not moving. It's practically at rest. So the speed at the A is 0. VA squared, this is approximately 0, plus rho GH. This is the height of that point A. Now this should be equal to, well, the pressure at this point. Well, this point is open. It's again P0. It should be P0. It is subject to the external air. So the pressure will again be the same. Maybe slightly different than P0, but mainly P0. Because you see, let's exaggerate it a bit. This is the hole, this is the flow. If the pressure here is not equal to P0, that means if you imagine such a small volume, there will, let's say the pressure here is larger than P0, this small volume will feel a force in that direction. And it will just move vertically up. It will accelerate upwards, but that's not what we observe. So the pressure here should be equal to P0.
Pressure trying to stop the motion is P0. The pressure trying to stop the motion is P0. There is no pressure from the liquid.
From the liquid. Well, if this hole is not there, if we close that hole, the pressure is P0 plus rho GH. No, I mean, this hole changes the pressure. When you dig this hole, the pressure at this point will change. It should change. Well, you see, the expression that pressure is equal to rho h times the height we derived using the stationary fluids. It doesn't have to be valid in this case. I mean, this argument just shows you, I mean, this is the liquid we have. So it will be flowing out. And if the pressure inside your liquid and outside, they are not equal, I mean, it will just expand. Imagine there is no hole. It was. No, when it reaches steady state, it won't be.
Wouldn't the pressure at the hole just be the pressure of the liquid? Since P out or the P naught is the pressure of the atmosphere, right? And inside the liquid, when there is no hole, then the pressure is P naught plus whatever the liquid pressure is. So when a hole is created, don't the P naught cancel each other out? The only pressure being left being the pressure of the liquid.
No, you mean here. But you see, this droplet over here, is it accelerating?
Not right now if there's no hole. Is it a hole?
Now there's a hole.
Oh, yes, it is. It would be accelerated.
Can you repeat?
You asked me if it's accelerated, right?
Yeah.
I said yes because of the pressure of the water causing motion.
So it says that right out of this hole and right inside that hole, the pressure should be different because there's acceleration, right? So it cannot be equal to the pressure right over here before there was a hole. And this argument convinces me, at least, that the pressure inside should be equal to P0. Because you see, otherwise, I mean, you probably have seen these things. I mean, when you don't completely open it, at the instant, the water, I mean, when you open this small hole, it doesn't just start flowing such smoothly. First, it just makes a mess. Then the pressure balances, and the pressure at this point just becomes P0. If it is not, the water would spread out. Instead of, it's not at rest. If it was, I mean, our previous conclusions were for fluids at rest. This is not at rest. This is flowing. There's acceleration, etc. So the pressure would be P0. The velocity, let's call it V. So this is what Bernoulli's equation tells us. Now P0s, they will cancel. The P0 has no effect. This is 0 anyway. So what happens is the speed is square root of 2gh. It is as if, I mean, you just drop of water from here, it comes here. I mean, if there was no liquid, if you just drop some mass from this point, when it reaches this point, this will have been its speed. And again, the same result is we obtain by the Bernoulli's equation. So now we know the speed. Now the next.
Through a small dust or a piece of something that can move the fluid. We throw it at a velocity 0. Would its velocity when it's exiting that will be 0 plus that?
Well, you see, what we are assuming over here, we made several assumptions. First of all, this point is not moving. So if you put some speck over there, its speed, it will take an infinitely long amount of time to reach this point. Well, because this point is, I mean, there is a huge amount of water and the leak is very small. Of course, you can take into account the speed at the top. The speed at the top will also depend on, well, you can include the speed at the top and correct this expression. And then, of course, this will not be true and your question will not be valid. But if you put some speck somewhere over here, flowing with the liquid, when it comes out, this will be its speed. Questions? Okay, the next thing that to be done, it would have been interesting if, for example, to answer your question also, let's say you have this container filled with liquid and you create a large hole, not a small one. Each, and of course you can calculate the velocity of the fluid at every point on this opening. So you can calculate how much fluid flows out per unit time, and you can calculate how much it takes for the liquid to drain out of this container. But I mean, we will not do that. We don't have time. Any questions? I mean, I will not be discussing any more topics today. Our time is almost up. So if you have any questions. Just inside. I would say close to P0. Now, one thing about the force that seems to be confusing you quite often is that you don't really have the freedom to exert a force or not, unless there is a resistance to it. And the same thing happens over here. You see, if the hole is not there, the walls of the container will be resisting the liquid over here. So the liquid will be able to exert a large force on the container. But if there is nothing to resist the force exerted by the liquid, then the liquid cannot exert the force. You cannot choose, for example, to push your friend by 50 newtons and your friend chooses to push you back by 20 newtons. You don't have that freedom. How does? Well, in this one, well, let's see. At the top, we said that it's not moving at all, more or less. So it's almost liquid at rest. So as you go deeper and deeper with H, the pressure will increase. Well, if you are close to this edge, I don't think the pressure would change from our predictions of a linear increase in pressure. If you are close to here, the pressure will increase. It will reach some maximum somewhere over here. And after that, it will start decreasing. And it will be back to its initial value. Lower, well, this is at the pressure P0. So this liquid over here will not move at all. So this is liquid at rest with a boundary pressure of P0, it will increase linearly from here to here. Of course, here it increases linearly from top to the bottom, more or less. Well, it will increase, but I don't think it will be linear. I mean, since we are assuming that the hole is very small, only in the very near vicinity of this hole there will be any significant motion. Only in that very small region there will be some deviation from what we had predicted, calculated for a stationary fluid. Okay, so see you on Monday. Don't forget the final exam.